All right, so welcome everybody to this Chern-Weil Symposium. Let me say a word-wise, it's very fitting to have this establish this new lecture series, the Chern-Weil series. Both Chern and Weil are obviously big figures in 20th century mathematics. Chern has been a professor at the University of Chicago for 49 to 60, very bit earlier from 47 to 58. So along with other people like Canderon, Zygmunt, Saunder, Marlins, March, and Stone, they represent this golden age of Department of Mathematics at the University of Chicago, so called the Stone Age. So with the generous donation from the ZhengTong foundations, you could establish this Chern-Weil Symposium. It happened first time before the pandemic, so we interrupted. We restart this year. We decided to have this event twice a year, one in the spring and the other in the fall. This is the fall 2024 Chern-Weil Symposium. So first, our first speaker is Camillo Lellis from the IAS Princeton. He speaks on the area of minimizing currents, mode and integers.
Thank you very much. It's a pleasure to be here. It's actually my first time here physically. I was invited give a colloquium, if I remember correctly, and then the pandemic kicked in, so I gave it online. So let me start by introducing the objects that will be the subject of my talk. So, so first of all, so you have singular chains, mod, and integer. Okay, and what we understand by this is that you have the usual singular chain. So, like, let's say one of these chains is T. So this is going to be the formal sum of finitely many integer combinations of. I'm going to actually use this notation over here. So this is going to be the push forward of some, say, simplex. So you have to think about delta I to just be a simplex of dimension m, and you're pushing this forward into some Euclidean space by using a C1 function. And of course, this one also can kind of add. Okay, and so these are actually integral chains, integral singular chains. So this is a finite linear integer combination. And now I want to fix an integer. Q, and I want to consider these coefficients mod Q. So I'm actually going to say that if I have this coefficient over here, or this coefficient plus an integer multiple of Q, actually, for me, the chain is exactly the same. Okay, once I have this, let me just make a little kind of better assumption. So assume the FIs are actually C1 embeddings, so that I'm not double counting the chain, maybe, like, I don't want to fold it somewhat. Okay, then I can also define what is the mass of the chain, or if you want, the total area. And what is this going to be? So this is going to be the sum for I equal 1 to n, and then I have to take a norm of this coefficient over here that I take. And the norm that I'm taking is...
Would you mind pushing the other board
just slightly higher? Certainly. Am I tall enough to do that? Yeah, I am.
Thank you so much.
Certainly. So, okay, and then here I'm just going to take the n-dimensional volume of whatever is this image. Okay, and I mean, you can easily imagine what I actually want to put over here. So what I want to put over here is the smallest modulo of an integer which is in the same class as ki. Okay, so just for instance, if I were considering chains mod 3, well, I can only put like coefficients which are 0, 1, and 2, or 0, 1, and minus 1, and 1 is going to get modulus 1, and minus 1 is going to get modulus 1 as well. Okay. So, okay, this is an interesting thing, and now what I would like to do, of course, I know what the boundaries of these objects are, so, the boundary of T, I understand it in the usual topological sense. So it still is going to give me a singular chain mod Q. And what I want to do, so the problem that I want to pose today is I would like to minimize the mass in some natural situation. So one situation could be, for instance, I prescribe the boundary. So I fix it, and this is what people call the plateau problem. But the other situation that I could consider a general ambient manifold, not necessarily like the Euclidean space. And in the general ambient manifold, I could minimize in an homology class. In this case, I would actually minimize among cycles which are in the same homology class. And of course, the first question that you could pose is, does this make sense? Can I find a functional analytic context in which I can actually prove that there is a minimizer? And so the answer to this question was first given by Federer and Fleming in the 60s. And so there exists a natural closure so a natural closure of these objects and in this natural closure, you have a functional analytic space in which you have enough compactness and good properties for the mass to say that there's always a minimizer. So let's say with good functional properties, so yielding the existence of minimizers. So what is actually the closure? First of all, I have to tell you what is the topology that I want to put on this space, and the topology is actually induced by a distance. So there's something that you could call the flat norm. So, and the flat norm of, it's really a norm, so if I tell you, but I want to kind of tell you on the difference of two guys, so that's going to be kind of interesting. So it's really a norm, so it's the norm of the difference of these two objects. So this norm is actually the infimum of the mass of, say, A plus the mass of B when A and B are such that S minus T is equal to A plus the boundary of B. Okay, so in other words, say S and T are close if I can add a little bit of a piece, like a piece like this, and make the white the white chain equal to the blue chain. So the distance is certainly going to be smaller than this small piece over here, and so this would be A. But another situation in which I want to kind of say that two things are sort of close to each other is a situation like this. Right? In this situation, obviously, I cannot just put a small red piece and make with little area. But what I could do is I could add actually two small red pieces over here, and then I actually discovered that this guy is a boundary, and so then I can fill in with the yellow piece. And the yellow piece for me is going to be the B, and the red piece is going to be the A. Right? So it gives you somehow the idea that two things are closed if I can like add a little bit of mass and somehow a filling cycle, a filling chain, and pay a little bit of mass also on the chain. Right? So this would be two one-dimensional objects, and I'm adding a little bit of A and this B to actually make this formula correct. Okay, so this is the distance that I can put, and the corresponding space which I find. So
a stupid question. So
yes.
Patinate 2.
Yes.
Is the distance 0? Like I mean, like one chain is like this, and then another one is this plus this.
Yeah, then it would be equal to 0. Yes, exactly. Yes. Yeah, I mean, if I really had kind of put this point equal to that point, then yes, I mean, the two guys are actually exactly the same. Okay, so now what you're going to do is, like, this gives you a distance. You can actually complete the space, and you have a pretty good functional analytic space in which you can minimize this mass. Of course, you could ask yourself, though, I defined it to you what the mass over there is. What is the actual definition of the mass in the general case? Well, I could go by approximation. So I could just tell you, like, fix your object in your closure. So this is the limit of some sequence which is converging to it, and kind of take the least amount of mass that you can achieve by taking all possible sequences that you go. So this is a kind of functional analytic definition of the mass. But actually, you have something better. So there is a description of the objects which are in the closure of that. And so this is one of the theorems of Federer and Fleming. So if, say, some S is in the closure, and I assume that the mass of S is finite, okay, then S has a very nice representation. So instead of adding a finite sum over here, I have to put a series. The coefficients stay the same. Then I can put push forwards of appropriate subsets, but unfortunately the push forwards are not going to be nice delta I over here, nice simplices in Rm, but they're going to be arbitrarily closed subsets of the delta i's. Now these ki's, these are closed, say, subsets of Rm. So in other words, before you were having like, cycles which might look like this, and now you might have actually cycles which look like, ugly subsets of these guys. And even more so like countably many. Okay, so you see before that, in our description, I had this thing which was some sort of, finitely many C1 pieces, maybe with corners or things like that. Now, in this case, I have countably many. And instead of really having like, C1 submanifolds or pieces of the C1 submanifolds, which are kind of nice, I have ugly pieces of C1 submanifolds. But nonetheless, when you package actually all together, so in analysis, you have a word for these type of sets. So this guy over here is what we call an m-dimensional rectifiable set. So you can think about an m-dimensional rectifiable set as a poor man version of a C1 surface. So the actual definition is that it can be covered by countably many C1 surfaces up to a set of measure 0 for the Hausdorff measure. And somehow, the set of measure 0 for me is not really going to count because when I compute the mass of this object, I'm essentially ignoring kind of pieces of measure 0. Okay? So now here's the real central question of this talk. So Okay, the Federer and Fleming theory actually gives you the existence of a minimizer in this kind of class of objects. This class of objects is not too distant if you're, a deranged analyst like me from a C1 submanifold, but still, maybe you were actually hoping that if I look at the minimizer of the mass, there's going to be some more structure. So you're not going to see something totally crazy like, I don't know, some Swiss cheese which gets mapped into your space. So the question that I want to ask, therefore, is the regularity of a minimizer of the mass in this closure. And this is what we call an area minimizing current mod Q.
Do you have a good notion of boundary in that class?
Sorry?
Do you still have a good notion of boundary in that class?
Yes. For instance, there is the one theorem that you have is the so-called boundary rectifiability theorem, which tells you that if the boundary has finite mass, it's again representable by countable union, by a rectifiable set and countable union and so on. And because it's you asking the question, that is the counterpart of de Giorgi's rectifiability theorem for the reduced boundary of a set of finite perimeter. And I guess I lost anybody else. But so it's a kind of like, kind of generalization of that, if you want.
You're going to give us an example where...
Yes. 1 second, and I'm going to actually give examples of all of this.
Yeah.
But you need finite perimeter to have a boundary.
Sorry?
You need finite perimeter then to have a boundary.
Right, that's why the theorem tells you if the boundary has finite mass, then it is
Then there is a
represented in the
boundary.
same way.
Yeah.
Yes. Yeah.
Otherwise, there
But
would be stuff
yes,
there
yes,
that
yes,
doesn't have any...
Sure. But you see, I'm interested either in the plateau problem, so the boundary is fixed, then I don't have to care about it, or I'm interested in minimizing in an homology class, and then the boundary is 0. So somehow, in the situations in which I'm interested in, I'm actually not really bothered by whether the boundary is regular or not. Okay, so now, there's a counterpart to this, in which, instead of playing this game with x integers mod q, I just allow any integer. Okay, and those are called integral currents. And I can actually play exactly the same kind of minimizing game. In fact, you can think of an abstract theory in which I give you a coefficient group and you can sort of minimize in that coefficient group. But if you want to get a theorem like this, then your coefficient group has to be sufficiently disconnected. I mean, it has to be something like the integers or the integers mod q or something anyway in which the elements are somewhat isolated, okay? But I don't want to go into that. On the other hand, it's important over here, so if the coefficient group is Z, okay, then you can run the same theory, and the theory gives you what are called area minimizing integral current. Okay, so examples. So here is an example. So a smooth surface with one coefficient. Okay, so that's an integral current, and that's, of course, also a current mod q. And you will have to take the coefficient mod q. Okay, so here is another example. So finitely many surfaces which are nice. Now this finitely many over here is going to be 3. And each of them come with some multiplicities k1, k2, and k3, right? So now at this junction, if I'm taking integer coefficients, there's going to be the boundary unless, so let's say that the orientations are done in the following way, right? So this is one orientation for one surface, this is one orientation for the other surface, and then down here I have another orientation for the other surfaces. Okay, so if I put this kind of orientations, then I would need k1 plus k2 plus k3 equals 0 to say that this one is not going to have a boundary over there in the sense of IntegerAbstract, right? So kind of like, all the boundaries that I get over there, they balance each other. But if I actually want something which is not which is an interesting current mod q, if the sum of these coefficients is equal to 0 mod q, then I'm not seeing this boundary, right? I mean, when I compute the boundary, I get a multiple of q, and by my stipulation, a multiple of q is actually equal to 0, okay? Because I'm taking coefficients mod q. So here's another example. Of course, the Möbius band, or like, I don't know, the Klein bottle. So this is a non-orientable surface, but it's a cycle mod 2, right? So I could cut actually along one circle, and then I have a perfectly legal cylinder whose boundary is going to be one copy of the circle over there and one copy of the circle over here. I'm actually attaching the Klein bottle, and if I'm using integer coefficients, I get a boundary which is 1 plus 1. So it's 2. So that guy has a boundary in integral coefficients. But in coefficients, mod 2 does not have a boundary, right? So it's without a boundary. So Klein bottle is a cycle mod 2. But now if I take, say, q copies of the Klein bottle, of course, this is going to be a cycle mod 2q. Okay? So, and these are other examples as well. Okay, so here is kind of the conjecture that you could advance. So, maybe a minimizer of the mass in that particular class. So you fix, I don't know, for instance, your homology mod q, and like, you run this argument, you close your space in the homologous cycles, you find a minimizer, and then the conjecture could be that the minimizer mod q is always going to look as in this example, if q is an even integer. So there's always going to be a bunch of codimension 1 nice surfaces, and you have nice minimal pieces which are actually joining at these boundaries, and then when they join at these boundaries, they have the correct multiplicity so that the boundary disappears. Or if you are even, there's also the situation in which you could be a non-orientable cycle with maximal multiplicity possible, which is q, like half of the multiplicity. Okay? So the conjecture would be something like any minimizer, say, in an homology class, or for a fixed boundary, so looks locally like, say, example 1, or like example 2. So this would mean at the local level, I always find, you give me a point, which is kind of in the support of this minimizer. So where I truly see, like, some of that junk over there, which is in S, and then there's a small neighborhood around this point in which I am completely smooth and the classical submanifold, or I am a picture like this. So a bunch of classical submanifolds which are actually joining at the common boundary in a nice way, and at the common boundary you have the correct multiplicity so that that boundary does not exist. Okay? So if I have it in homology class, I have no boundary. If I have a fixed boundary, I just have to stipulate that this is the picture that I see when I am away from the fixed boundary that you gave to me. Okay? Away from the fixed boundary. Okay, if you have such powerful theorem at the local level, then you can actually mount everything at the global level, and at the global level you can decompose your minimizer, if you have no boundaries, for instance, in two pieces. So there are kind of non-orientable pieces which are taken with the maximal multiplicity if your coefficient is even, or otherwise there's like, some global guys which are meeting at some global common boundary with some constant multiplicities. And, this global boundary is going to have these multiplicities which are going kind of to be frozen constant along the connected components of this piece. So another way you can actually think about this is that it looks like what people in analysis call a free boundary problem. Okay? So if you don't have the mod Q integer, you're just looking for a membrane which minimizes the area, for an orientable guy which minimizes the area. If you introduce actually this modulus Q, what is happening is that you have the freedom of locating an n-1 dimensional guy and then attach the minimizers to this one with some special stipulation that when they come over there, their multiplicities have to become multiples of Q. Okay? So you could call it as a geometric free boundary problem. Anyway, so certainly the conjecture is false, so the picture is more complicated. So here is another example. So let me call this example number 4. And, well, I mean, here you could worry whether, can I make these examples really minimizing? But it's pretty obvious that I can make them minimizing, right? So if you think about the cross-section of this, for instance, it looks like a triple junction. So if I give you, 3 points over here, all with positive multiplicities, and I ask you, join it in a current mod 3 in the most efficient way, you will actually find 3 segments which are going at 120 degrees on a common center. It's very easy to do this, to prove this. So all of these situations actually can occur. It's a bit more difficult to actually show that this one can occur, but this one can occur as well. But here, let me show you an example which is way more interesting. So take the plane, and then take a function f of x, which is going to look like this. So it's going to be x1 squared minus x2 squared plus higher order terms. Okay, the reason why I need the higher order terms for the analysts is because I want to solve the minima surface equation. So I need somehow some higher order perturbation to do that. And so what you're having a saddle point, right? And now, probably a little bit bad at drawing pictures, but your surface is sometimes above the, it's sometimes above the blackboard, and then I guess on these other guys it should be below the blackboard, but I'm not sure I'm actually able to really draw this. So in here you are below the blackboard, right? So here is going to be above, and here is going to be below. Okay, but the important point is that when you look at one of these rays which are getting out from the origin, so you're seeing 4 surfaces which are attaching to that ray, right? I mean, you're seeing one triangle and another triangle which are flat, and then one triangle which comes up and another triangle which comes down. Okay, so I have actually 4 pieces which are coming jointly at this line. And now I can give multiplicities in such a way that, they sum up to 4 on that particular line. So I can make this picture, so the union of graph of f and plane a current mod 4 or a cycle mod 4. Okay, and there is a deep theorem by Brian White. I think this is something like 78, which tells you this is a minimizer. And so this is a minimizer, and in that particular point, what you're having 4 of these interfaces, if you want, 4 of these interfaces which are coming together at that point. So you certainly cannot hope to have a conjecture like this, because if I am understanding kind of, these codimension 1 junctions as singularities, so these are codimension 1 singularities, but they themselves could actually come together at codimension 2 singularities. So you could and you should modify this conjecture by saying that any minimizer in an homology class or in a fixed boundary looks locally like example 1 or like example 2 away from the fixed boundary. But here you should better say something like up to some exceptional set of codimension 2. So codimension 2 in your object. So if your object is 2-dimensional, this exceptional set consists of maybe points. But if your object is 3-dimensional, this exceptional set now could consist of lines. Whereas, of course, the junctions could consist of 2-dimensional surfaces.
Just in this example here,
Yes.
I'm always going to be confused what the boundary. Here's the
boundary, of course, you could in principle kind of continue your functions at infinity. So it's a huge, complete surface. If you cut it with a ball, of course, all of the boundary is going to be on the sphere.
So, for example, in this situation, if you just cut it with the sphere, make that your boundary, and then ask for a thing.
Yes, exactly. So cut this guy with a sphere. You have a 1-dimensional object, which is a cycle mod 4. The minimal filling is given by that example. And it has a singularity at the origin, which is more complicated because you have the interaction of codimension 1 singularities which are getting inside. Yes?
I can ignore the higher order terms, my personal.
I mean, the higher order terms are higher order terms in the Taylor expansion. So, okay, so I'm a PDE guy. The point would be that this function would satisfy Laplacian of f equals 0. That's not the correct PDE for minimizing the area functional. The correct PDE is this guy. But you see, when the gradient of f looks very flat, which is going to be what this function looks, this one is a kind of higher order terms, higher order perturbation, and so you're almost harmonic. Okay? So yeah, you can ignore that. I mean, if you really want to insist, there's going to be, for instance, a complex analytic representation of what that function f should be through Weierstrass representation. Oh, and by the way, there's many ways actually of putting the higher order terms in such a way that you actually solve the minima surface equation at that point. Okay, so it's not uniquely determined. But the upshot of the theorem by White is that it doesn't even matter what higher order terms you're putting somehow there. As soon as you solve the minimum surface equation, actually, the union of the two graphs is going to be a minimizer mod 4. Okay, and well, what's the main theorem that I just want to kind of go through in this talk? The conjecture is correct in any dimension and codimension. So, and the story is somewhat long.
All right, I'm going to interrupt again. So,
yes.
In some very infinitable plateau problem where you don't even have these congruences, and then you try to get some minimum.
Yes.
Will that minimum only have codimension 1 singularities?
Okay, so now are you still allowing me to put kind of codimension? I mean, are you still allowing me to put?
Just say my boundary is a bunch of circles.
Yes, this could still happen. I mean, it could still happen that you have a singularity in there. So let me give you a very concrete example. So if I give you three, so this is an example by Gene Taylor in the 70s. So if I give you three circles, and I put the circles correctly, the minimizer mod 3 is not going to be three disks, but it's going to be a surface over here, another surface over here, and this disk. And somehow my drawing is bad, so these three surfaces should come at 120 degrees over here. So this one is at 120 degrees. So here you have a kind of, nice boundary which consists of three curves which are kind of smooth. And if you actually try to find the minimizer mod 3, you will create two pieces of catenoids. Those are actually the actual name of the surfaces that you will find, and the middle piece, which is a disk. And they create a boundary mod 3 on this circle. Okay, so...
Can I also ask a question about the theorem? So
yes.
You explained that there is this closure of the set of singular chains mod Q.
Yes.
And elements are represented of that form. How unique is that representation?
That's not going to be unique.
But it's possible to say when...
That's not going to be unique because, the sets that I allow you to use are so shitty that, you could kind of decompose them into two pieces and I can come up I take your decomposition, I take one of your two pieces and I decompose it even in a very bad way and then I find another representation. Yeah. It's very, very far from being unique.
But there's some equivalence relation. I mean, one can say when choosing.
Right. The equivalence relation is you take, your representation, my representation, you subtract it, and that is equal to 0. Yeah. I mean, one thing which I swept under the rug is that you want to pass this kind of concept of being, for instance, a boundary or a cycle mod Q to the limiting thing. That can be done. There was actually but it's an interesting question in analysis. In fact, there was an open problem for a very long time, which was solved by Robert Young some 6 or 7 years ago in the area about representing general guys. Okay, so maybe let me put over here. So the conjecture is true in any dimension and codimension, and for every integer q, so certainly this trueness is in the way you would expect it in codimension, for hypersurfaces. So for cycles in codimension 1 in your ambient manifold. In higher codimension, I'm going to tell you that there's a little caveat. Okay? Very well. So let me start with kind of history.
Sorry. Even in dimension 2 with surfaces, so codimension 2 is points.
Yes.
But could it be like an infinite number of horrible points or finite number?
Okay, so you're kind of getting to... So what we can prove is that it's rectifiable. In the case of points, they could be countably many. In points, not that I don't think so. And in points, maybe we can squeeze the... in the case the lower dimensional set is really points, I think you can prove they are isolated, actually, by using our techniques. But when you actually start looking at three-dimensional objects, and this exceptional set could be lines, we're very far from telling you it's really lines. It could be an horrible set, but at least an horrible set which I can cover with countably many lines. Yes. Okay, so first of all, Q equal 2. So Q equal 2 does not even have the Q equal 2 So Q equal 2 does not even have the problem of the junctions, right? I mean, you don't have enough coefficients actually to have a junction. So you can only have kind of non-orientability. And so Q equal 2, Federer already was able to prove that back in the 70s. And if you're really insisting in this rectifiability thing, that is Leon-Simon in the 90s. Okay, so now it gets more interesting. So Q equal 3. So Q equal 3 in the lowest, the easiest situation. So two-dimensional objects. Let me ignore that I can put a Riemannian manifold. Let me just say in R3. So this is 1973 by Jean Taylor. And it's much better than that because it's a very special case. So that something like this actually cannot happen. So it's really like, you know, a bunch of curves which are separated. So they cannot come together at points. So there is no exception to this. The conjecture would have been true in the initial formulation without exceptional sets. Okay, then Q equal 4. Oh, no, wait. Let me just finish. So Q equal 3 for hypersurfaces so again in codimension, so m-dimensional objects in Rn plus 1. So this is the work of Leon-Simon at the end of the 80s. This way. And Q equal 4 hypersurface. So Q equal 4 and hypersurface. So this is in this paper by White. Okay, and then the subject was essentially dormant for quite some time, and what happened is that the theorem that I told you is the combination of several works. So myself, Jonas Hirsch, Andrea Marchese, and Salvatore Stuvard. So our first paper, I believe this was like in 2018. Oh, maybe I should have said though something else also. So Q odd and hypersurfaces. Now there's a partial result. By White in 86. And so by partial result is that this awkward kind of rectifiability, which is not quite being C1 submanifold, can be proved by using his stuff and something which is called Neighbor-Valtorta theory, which comes much later, so in 2016. So to give you that, okay, the first singularities, they're not exactly C1. I mean, you're not able to prove that in that way, but rectifiability you can get. Okay, so now this actually does several things, but one of the things that it does, it solves Q odd for general codimension with the same partial result over here. Okay, so then we have a subsequent work with Spolaor. So there's a strange combination in the literature because there's a work by us, and then there's an important contribution by Minter and Wickramasekera. Then us again. And then my student Anna Skorobogatova. And the union of all of these results give you every Q for hypersurfaces. Okay, and then finally, this year, or last year? No, maybe we put it on the web this year, actually. So the general case of every Q and every codimension, it's a paper by Anna, Paul Minter, and myself. So this covers like really the theorem in all possible situations. But I told you that there's a slight difference between the higher codimension situation and the codimension one, hypersurfaces. And what the slight difference is the following. So we're able to prove that the first stratum of singularities is a nice C1 surface. So say that we were a two-dimensional object, the first singularity is really a curve. And so now, for hypersurfaces, this curve really comes over here, and there are three, or n objects which are coming, and they are all coming with nice kind of boundary over there. So they are all attaching, like you would really picture yourself without any foul play. So three surfaces which are coming over there at different angles, and that's very important. So when they are coming together at different angles. They cannot come together kind of tangentially. And for the PDE experts, the reason why this actually cannot happen in codimension 1 is because the PDE has something which is called boundary maximum principle or Hopf maximum principle, and that's where we're using the hypersurface case. Now, what might happen in higher codimension is that the surfaces, they are coming kind of, over there, but maybe they're kind of passing each other at the boundary, or maybe they can come kind of tangentially, so the boundary behavior is more complicated. So I can tell you that this boundary curve is smooth, but I cannot really tell you that the local picture around this boundary curve is a diffeomorphism of a triple junction, for instance. It might be more complicated than that. So, for hypersurfaces, around the point here, let's say P, around P, the object is diffeo to finitely many planes coming together at a different angle. Okay? In higher codimension, there's a question mark whether I can really prove you that you're diffeomorphic to that situation. It might be more complicated. But the junction is smooth. That's what we can really prove. So let me just sure. Okay, so my time is actually almost over. Let me tell you what are the difficulties and what went into kind of this history. So one of the difficulties which people didn't have to face at the very beginning when they were looking at low numbers, so a number like 2 or a number like 3, and to a certain extent even a number like 4. So is the following, and in codimension 1. So in the lucky situations, there are no flat singularities. So what do I mean by flat singularities? If you take the example that I gave you actually before, so this example in which I have the union of the graph of the function g, which is identically equal to 0, and of the function f, which is equal to x1 squared minus x2 squared plus higher order terms. So you will notice that at this point over here, if I zoom into my singularity by applying an homotity, because there is a second order of contact between this function and that function, when I'm zooming in by making homothetic rescalings, the upper function is going to collapse on the lower function. Or the x1 minus x2 squared function is going to collapse on the 0 function. So what I want to say is that in the language of geometric measure theory, at that point, I have a tangent plane with multiplicity 2. And in several other situations, knowing a priori that you have a flat tangent plane in some weak sense actually guarantees you regularity. But in this situation, it does not. Okay, so in other words, so flat singular points are difficult to analyze. Okay, so in codimension 1, so when you actually start looking at that series of papers that came over there, so there was a very interesting and very simple elementary fact, which I want to share with you, which essentially was our starting point. Okay, so let me go a little bit slower, actually. So,
for example, when you do the blow up at the singular point,
yes.
Do you get like double the multiplicity, or
I get double the multiplicity.
Or do they cancel out?
No. I get double the multiplicity. I get actually
so it's a
2 copies of
multiplicity is a non-zero number.
Yes. And that is actually what is always happening. So all of the examples in which I have a bad flat singular point, I have to pick up a multiplicity which is higher than 1. Okay, so what happened over here somehow is that because of previous works, which I had with Emanuele Spadaro, so in the case of coefficients which are not mod Q, there was a theory developed by Arndt to actually deal with these guys and show that they are not too many. And what we did, after working out a version of this theory which is comprehensible to the world, in here we actually managed to apply it to the situation of mod Q currents. So, in a sense, we were able to kind of get rid of this problem of flat singular points, but not really in all of the situations. So in the situations in which these flat singular points don't interact too much with the codimension 1 singularities, with the lines, if you want, dimensional case. So it wouldn't allow us actually to go too much further. And what happened over here, which is what we realized in codimension 1, but even in higher codimension, is a very interesting and simple remark. So in general, at junctions, the multiplicities sum up to either Q or minus Q. So what do I mean by this is that in each of the things which are actually coming together, these multiplicities, I can identify them by, the minimal element which is kind of representing this element in the group mod Q according to my norm. So in principle, over here, I would actually be allowed to sum these multiplicities to, 2Q, 3Q, 4Q, whatever you want. But the minimality property actually tells you that you're not allowed to put 2Q over here or minus 2Q. You only can sum up to Q or you can sum up to minus Q. And you cannot sum up to 0. I mean, if you sum up to 0, then you would be kind of a classical integral current and you would be able to resolve the singularity. And so this was actually quite important because we realized at that point that you can actually apply theories developed by Leon Simon and Chern-Weil to actually go further in the codimension 1 situation. And when Paul Minter and Neshan actually picked up this idea, they realized that in fact they can prove a much more general theorem by exploiting this structural result. So their theory applied to what are called stable hypersurfaces. Okay, and that's kind of somewhat close to the hypersurface case. And okay, the higher codimension is a very recent development of last year, and it's actually due to the fact that I told you that in the case of area minimizing currents, we can use Angren's theory in the mod Q case, but in fact, even in the area minimizing currents, we were able to go way beyond Angren's theory, and that is actually what is entering in this last piece. And I don't want to actually go extra time. Maybe I already went extra time. So yeah, let me thank you for your attention.
Question? Again, maybe a really basic question. So, in some situations, when you're trying to do minimization and you want to study the singularities, I mean,
yes,
is this ultimately like a local thing? Like you could really just look at this.
Yes.
So it's a purely local thing.
Yes.
And you're trying to deform.
Yes, this theory is a purely local thing. Now, although one thing which I maybe hinted at, and I didn't tell you maybe too specifically, you can kind of do something global as well. So you can, for instance, use this global theory to, for instance, tell you something like this. If you give me multiplicity 4, I can see both kind of the non-orientable picture, or I can see the picture in which there are singularities which are coming this way. But this has to happen for two disconnected components. So in multiplicity even, there will be some connected components which are kind of nice, smooth, and non-orientable with the top multiplicity. So if Q is equal to 4, then these are kind of double cover of non-orientable surfaces. And then there is another piece, and in that piece you might see junctions, but they're junctions coming with multiplicities 1. So even though the theory is local, there are actually some global conclusions that you can get from it.
I was running my bell.
Can I say why you cannot get 2Q?
Yes. So this is really a silly elementary observation, but the point is something like this. So if I really have too many, like for instance, let's say that Q is equal 3, and then I have 1, 1, 1, and then 1, 1, 1. Then what I can do is I can kind of make this shorter. And here I have 1, 1, 1, so this one doesn't create any boundary. And here I have 1, 1, 1 again, and this doesn't create any boundary. And now, of course, this kind of cannot be a minimization problem. So your membrane should better instead look like this. So, and now you just have to imagine that it's a very simple combinatorial kind of observation that if it is 2Q, there's going to be a hyperplane which is going to cut my current into two pieces, and I can assign multiplicities in such a way that the two pieces sum to Q separately. And then because I am on either side of the hyperplane, I can simply move the singularity and gain in area. So this is in codimension. This is really if you have lines. Of course, if you have a full surface, what I will be able to do, I will be able to improve a little bit over here, open up the singularity, but then I have to join the singularities again back because maybe I have to match boundary data. But that is not a difficult thing.
Full of not looking like the nicest possible picture in higher codimension. In this, over there, you wrote that for hypersurfaces, it definitely looks like.
Yeah.
Is it easy to write down an example where it doesn't happen in higher codimension?
So yes and no, meaning the following. So so I have a PhD student who, in his PhD thesis, has created an example of the following type. So there's an area minimizing integral current with a boundary. The boundary is a perfectly nice two-dimensional plane and taken with some multiplicity. And there are pieces coming over here which are not coming at different angles, and they interact on a singular point in some kind of complicated way, doing some branching. Now, this is an example with a boundary. What you could imagine doing, but I don't know if it's going to give you a minimizer, is to take that picture and paste it, by making some symmetries and paste, 4 of them and making a current mod 12. So is that going to be then minimizing or not? This is a very tough question because in general, it's not that easy to actually show you that something is an absolute minimizer of a functional, right? Even on a finite dimensional situation, what do you do when you give an exercise? People compute f prime equal to 0, and then you insert, you insert the values, and you see where actually the absolute minimizer is. But this is a way more complicated situation. So it's conceivable that the theorem is in some sense optimal because along the boundaries there might be some points which are behaving badly. But so far, we have an example which is only behaving badly for a straight boundary in a sense, without knowing how to continue on the other side.
More question, let's thank speaker again. Let's resume in 5 minutes.
Timer's up.